Welcome to this explainer. Today, we are diving straight into the invisible mathematical language that allows a computer to actually recognize human emotion in music. If you've ever wondered how your streaming app just kind of knows exactly what mood you're in, well, you're in the right place. We're going to discuss the specific features used in details in the Music Emotion Recognition task, or MER, and look at exactly how algorithms decode our favorite tracks. But before we start peeling back the layers of a song, we have to ask a genuinely fascinating question. How exactly does a cold, calculating piece of code feel a song? I mean, we experience music as this deeply subjective, bodily thing, right? We get chills, we tap our feet, our hearts swell, but a machine, it just sees ones and zeros. So how on earth does it translate a raw digital audio file into a profoundly human feeling like nostalgia or joy or pure aggression? To figure that out, here is our agenda for today. We'll start with the emotion grid, then look at acoustic building blocks, explore the power of lyrics, track the body's response, and finally wrap up with the multimodal future.
All right, let's jump straight into section 1, the emotion grid.
So before an AI can even begin to extract features from a song, it absolutely needs a map. It needs a standardized compass of human feelings. Enter Russell's circumplex model. This is basically a framework from psychology that acts as a translator, turning our really subjective feelings into hard, measurable mathematical coordinates on a 2D plane. Instead of trying to teach a computer 100 different subtle mood words, researchers just simplify the whole shebang. The x-axis represents valence, which is basically just how positive or negative a song is. And the y-axis? That represents arousal, the energy, the tension, or the excitement level. By plotting valence against arousal, researchers can drop the vibe of literally any track into one of 4 distinct quadrants. It's proof that even something as messy as a mood can be quantified. Quadrant 1 is high energy and positive, so your happy, exciting pop anthems. Quadrant 2 is high energy but negative, perfect for when you're stuck in traffic and just need some aggressive heavy metal. Quadrant 3 drops down to low energy and negative. Think sad, melancholic ballads. And Quadrant 4 is low energy but positive, so calm, relaxed, acoustic tracks. This grid right here, this is the ultimate target every single algorithm is trying to hit.
Which brings us to section 2, acoustic building blocks.
Now that we have our map established, let's look at how algorithms actually plot a song onto that grid. The foundational layer here relies on low-level acoustic descriptors, or LLDs. These are the absolute raw data points that service the machine's basic vocabulary. We've got the root mean square, or RMS, which essentially models the local energy or amplitude of the track. Then there's mel frequency cepstral coefficients, or MFCCs, which is absolutely crucial because it captures the actual timbral qualities and shape of the sound. Add in things like the zero crossing rate, the tempo, and the spectral flux, and the machine literally starts to hear the raw physics of the audio.
But how do those numbers become feelings? Well, algorithms hunt for specific patterns in those features. For instance, if it detects jagged, high-energy RMS numbers and sharp spectral peaks, that's a dead giveaway for aggression or intense joy. On the flip side, if the machine picks up on low-frequency dominance with super soft transitions and a slow tempo, well, those features scream sadness or melancholy. And if it spots moderate fluctuations with smooth harmonic progressions, that maps straight over to the calm or romantic quadrant.
Then building off those raw waveforms, the extraction process scales up to mid-level perceptual features. You can think of these as a bridge. They mathematically describe the more advanced musical concepts that you and I just naturally understand without thinking about it. We're talking about 12-pitched chords, rhythmic complexity, and perceived melodiousness. By tracking how a song shifts chromatically over time, the algorithm finally starts to understand the actual harmony of the music, not just the raw bouncing sound waves.
Move on to section 3, the power of lyrics. Because, let's be real, a song isn't just instrumentals. The vocal performance carries a ton of the emotional weight. While acoustic features are busy measuring the physical sound waves, the tempo, the timbre, the pitch, textual features are doing something completely different. They analyze the structural meaning and sentiment of the actual sung words. Relying purely on audio is a rookie mistake. Think about it. An upbeat, major-key pop song might actually have incredibly dark, depressing lyrics. To truly map the emotion, the machine absolutely has to read the text. To extract those lyrical features, researchers bring in the big guns, massive, deep learning neural networks like BERT, DistilBERT, and Roberta. These models are wild because they automatically read and understand the emotional context of the lyrics without any human sitting there tagging it for them.
They spot slang, extract semantic sentiment, and, actually this is my favorite part, they even do structural analysis. The machine can independently figure out the emotional weight of a repeating chorus versus a narrative verse. It's pretty mind-blowing.
Okay, Section 4, Tracking the Body's Response. We've covered the audio and the text, but perceived emotion is just one piece of the puzzle. What about induced emotion? What we actually feel in our bodies? That is the holy grail. This creates a biological pipeline where the invisible magic of a song literally becomes hard data. First, a human subject listens to the music. Second, an EEG records their brainwaves, while an EDA device tracks changes in their skin conductance, basically sweat gland activity. Finally, algorithms take all those physiological features and map them right back to that valence and arousal grid we looked at earlier.
And we aren't just looking for generic excitement here. The AI is extracting very specific biological features. Metrics like EEG frontal asymmetry, which compares the left and right hemispheres of the brain, give the algorithm a direct VIP pass into your emotional processing centers. They also pull Horth mobility parameters to check signal variances, and they filter the EDA skin conductance data at exactly 0.6 Hz. Why? To clear out all the static noise and capture the pure, raw biological arousal happening in real time as the track plays.
Finally, let's look at Section 5, the multimodal future. So we've got acoustics, lyrics, and biology. Now, you might be totally surprised to learn that despite all this crazy advanced tech, traditional music emotion recognition has historically hovered around just 75% accuracy. Seriously, compare that to standard speech recognition, which sits up around 85 to nearly 100%. Why the gap? Because music is just incredibly messy. The layered combination of vocals, instruments, tempo shifts, and cultural context is a giant puzzle. But by fusing all these modalities together, training an AI to look at the waveform, read the text, and predict the biological response simultaneously, researchers are finally pushing past that 75% barrier. And here is where things get really crazy. As researchers master these multimodal features, they've realized they can actually run the process in reverse. Once an AI understands exactly which acoustic features, like a specific MFCC profile or a certain rhythmic flux, trigger a sad feeling versus a happy one, it can artificially manipulate them. They can take a song that sounds inherently joyful, tweak the underlying mathematical features, and seamlessly shift it to sound deeply, profoundly sad.
Which leaves us with this final provocative thought for today's explainer. As algorithms learn to perfectly translate our biological and acoustic features, they stop just being passive listeners. So what happens when they start actively composing music specifically designed on a microscopic mathematical level just to control our feelings? It's a fascinating and maybe just a little bit terrifying frontier. Thanks for joining me on this deep dive. Keep listening closely, and I'll catch you in the next explainer.